All right, welcome everyone. Today we're going to get started looking at our triple integrals, right? So we have done double integrals, integrating underneath some surface over some general region, like we did in 15.2, 15.3 from our text. We talked about integrating using polar coordinates for that region, right? When it was more circular kind of symmetry, using the r theta notation, and we saw how that changed, that altered our integrating factor, that dA became a r drd theta. So now we're going to transition into dealing with triple integrals. Okay, so let's jump into that discussion. All right, so for our triple integrals, okay, let's think back in this case real quick, right? In our beginning of the discussion, our double integrals, integrating over some region D of some function of x, y, d, a. And typically, when we saw those, we kind of visualize this. This is the volume under that surface f of x, y, right, over that region D. Okay, and so we visualized the problem if we had this region D over which we were integrating, and we have our surface here. Okay, imagine to some degree transposing that region D, but our idea was that we would take this little segment DA, some area from that region, and imagine building this kind of column of volume to sum up, right? But the big point was we'd have that DA, that little block, that little rectangle of area in that region D, where it had some dx, dy components, right? Some little width, some little height in those directions to compose the dA. So now, for these triple integrals, we can visualize summing, right, adding together the volumes of little blocks or cubes dV throughout a kind of 3D space. And so what I start to attempt to draw, okay, that now if we have some three-dimensional figure, three-dimensional surface, okay, let's do like what the book does. Let's say we have this space here. Okay, so this is this little floating blob out there in space. Okay. Now what we kind of imagine doing is that we're going to have inside of this this little cube, this little dv. And we're going to take those throughout and kind of start to build up. And again, it's almost like having those columns we had done before, but taking all these little dv and accumulating those, adding those up, stacking them up, if you will, to fill that space. Okay, so here we fill that 3D space with those little dV blocks, right, of volume. Okay, and so when we start to organize those, what's going to happen is that we can start to take this triplet integral over, and I think what the textbook does to use this space E. Okay, so we're going to integrate throughout that space E of, and then we can apply some function of 3 variables now over this dv. Okay, and so now trying to give a physical meaning for this might be a little bit harder because it's not like we're just computing the volume. We're taking that volume and acting upon it. We have this function multiplying, right, that volume. So some of those applications, right, if we're trying to find the mass, center mass, so on, if there's like a density function, the different densities throughout that region, depending on where we are, X, Y, and Z, maybe it's more densely compact material at the base than it is at the top, or vice versa, right? We can multiply that density times a little bit of volume to find out how much mass is in that space, and then start to add those up. We can find the total mass of that surface based on that density, okay? And there's other applications with those students taking our physics 3B, right, the electromagnetism, trying to find how much electric charge is accumulated on or in this surface in that region, that kind of charge density times the volume, that kind of concept. Okay, but the way I kind of think it, we have this function, this action that's being applied throughout that volume, and we're kind of accumulating all that net effect. Okay, but as we start to see, when we start to build those calculation wise, interpretation wise, at the moment, we're taking all these little blocks of volume, trying to fill that space and adding up all those components. Okay, and so we'll get into this moment here, right? And so summing up all those little dV in that 3D space, which I had labeled before E, right, will give that volume of the space. Okay, so the volume of that region E is just equal to this triple integral over E of just the dVs, right? So adding up all those little blocks, no function here, or you can imagine your function is just a constant one, the same density throughout, if you will, right? So without the function, that's just a dV, okay? And then a more generalized concept is if we have the function acting on those. That's what we mentioned before, okay? But we start doing this when we see that integrating factor dV I'm thinking about it. I should draw this like so. Okay. So there's our dv. What we can imagine is we have the same as before, dx, dy, dz. So we can organize you can write that integration in 6 different ways. Right? We can see that dv can just be alphabetically dx, dy, dz. It could be dx, dz, dy, right? Just kind of switching the order, the permutations, if we've taken statistics and so on before, right? Because depending on which variable we're going to integrate with respect to first, the other two outer integrating factors, right, will be held constant while we let x change, x vary. Or we can do, right, dy, dx, dz, dy, dz, dx, and lastly dz, dy, dx, dz, dx, dy, right? So there's going to be 1, 2, 3, 4, 5, 6 total different ways we can organize. Okay, and so this is when that graphing of some of those three-dimensional surfaces is going to show up, right? What we talked about back in chapter 12, section 12.6 in particular, right? Graphing some of those quadratic surfaces and so on, graphing some of these three-dimensional surfaces. This is where it shows up at the start, okay? So now, depending on our 3D space E, we can sketch to help find which organization of that dv, right? Which of those permutations would be best to set up and actually evaluate for that integral, right? Because depending on that orientation, depending on how that surface and region look, it might be easier to integrate with the z first and then deal with the x and y, right? Because then we figure out, okay, what does z range between? And then we start to look at that dx dy, just like we did with our double integrals. We have that region that we're projecting down into that xy plane. And it's that same concept. So it's kind of like that slowly decomposing that region, that space, to figure, okay, what's going to be the best organization? How can I find those limits on x, y, and z? So that way, once I actually see my expression they integrate, they kind of meld together. I can integrate my interior with respect to z first, let's say, and get some result that's going to be easy to integrate with respect to y or x next. Okay, and so as we go through this, is some kind of ideas, and we'll look at examples. All right, and our kind of quick, I'm going to say here simple, because they're not always going to be simple, and even these problems aren't simple, right? But in quick simple problems, all right, all of our limits of integration may be constants, right? So we might get a case when x goes between a to b, y goes between c and d, and then d goes between e and f, let's say, right? So that's kind of like having, we're going to be integrating inside a rectangular prism. Okay, kind of like we did with our double integrals. Maybe we're just integrating over a set rectangle. X goes between a certain pair of values, Y goes between a certain pair of values, right? So then our triple integral is just simply going to become, and again, depending on how we choose to organize, if we go, right, like dx first, it's going to be between a and b, dy, ct, dz, e to f, right? And then we can reorganize how we wish, just make sure you maintain that order, that organization of what limits go with which variable, right? But more commonly, our problems, our applications will have limits where the limit depends on our other variables, right? Where there are functions of our remaining variables that we have to integrate with respect to. And just remember the way I kind of dealt with before, our very last or outer limits of integration will be, should be constants, just numbers, right? And so a quick discussion and then we'll look at an example, okay? And again, depending on our region over which we're integrating, that surface, so on, we might have to take a look and see, okay, what's going to be the best organization, the best bet. But it may be a case when, as we look at these, let's say, for instance, if I'm going to integrate with respect to z first, right? And again, that z is typically like the height component. If we start to draw those, okay, maybe that's going to be a function of x and y. I'll say h1, h2. And so that's kind of like finding the height, right, between two surfaces, below this paraboloid, above this plane, above this other surface. That may depend on just x and y, right? And then we'll have a dy next, let's say. So then I'm doing the y direction. And so again, going back to like our math, our first semester calculus, right? Or maybe a little bit thought into our beginning of double integrals, where that y, right? Those two curves that we're using to bound in that xy plane, area between two curves, we can have some function, I kind of skipped out, but like g sub 1 of x, g sub 2 of x, some function of x there. But again, it could be a constant, maybe it goes from y is 0 to that function, that line in x, okay? But for the very outermost integrating factor, that should be constants, okay? So that way we get a kind of real number, tangible result in this calculation. And depending on how we organize, sometimes it might be easier for these kind of components to have some function in terms of, you know, x and z or y and z instead. So you just have to remember, okay, if I'm going to integrate for the z, I shouldn't have any z's left over after I evaluate. So that function, my limit shouldn't depend on z at all, but those later in the integration sequence. And so if we rearrange, the same concept goes. So in creating these, we really do have to kind of get a better idea of what that region that we're integrating over throughout looks like, okay? And so we're going to have to kind of utilize that idea of taking those heights, those widths, okay, for these columns. All right, so let's take a second here and let's do some examples evaluating triple integrals, okay? So for example, borrowing some of these problems from the textbook, right, that calculus at early transcendentals by Stewart, the 8th edition, okay? Let's check out this problem. This is problem number 10, page 1077 for my text. And we're going to be integrating e to the z over y dv throughout that 3D space E, where E is the set of order triples where y is between 0 and 1, x is between y and 1, and z is between 0 and this product xy. Okay? So as we notice, right, kind of thinking back, all right, notice for the y, these are all constants. So I'm thinking about integral, okay, my dv, this is going to be my last piece, my last component. For my x component, right, this depends on y only, then the other's a constant. But then for the z, depends on both x and y. So when it comes to looking at my dv, that means I should be doing dz first, dx in the middle, right, because it still has some variable dependence, and then my constant at the end of dy. Okay, and there's our function which we're integrating with respect to. All right, and so then with that, let's think about the region, all right, this 2D over which we're integrating. So this is like that region D that we talked about with our double integrals. If I look at the xy plane, all right, so look at the latter component, the dx dy, that's like my dA. I look at that region, well, y goes between 0 and 1. So there's my y. Y ranges between 0 and 1. Then x goes between the y and 1. Here's 1 on my x, okay? And if we see that x goes between y and 1, right, this is like, this is the line, y equals x. So we're kind of looking at 0, right? So when we hold y constant, when y is equal to a half, okay? X can be a half, and we're going to go from that point out to 1. When y is 0, it can go from 0 all the way to 1. So our region over which we're integrating is this space. Again, I'm kind of thinking about here. That will be my little rectangular strip that I talked about back in our double integral discussion, right? So we're going from the lowest y out to 1. Lowest, upper, right? So it's going from starting there, going out to x is 1. So this is that region. This is that region of which we're integrating. And then taking a second here. Okay. Y is going from 0 to 1. We have that line, y equals x to 1. So again, we're talking about this space. Okay. And then over that, right? Now we have to consider that z goes from 0 to the surface x times y, right? And that may take some time to kind of think, well, what does this look like? Okay, right? Along this path, when y is always equal to 0, right? X times 0, 0 still. When x is equal to 1, then y just follows. So we're going to kind of climb up to that z value 1, right? 1 times 1 is still 1. Thinking about how these are going to look, right? X and y are the same along that line. That's the line y equals x. So it's like an x squared, so it's like a parabola. So again, it's this kind of shape we have to consider the surface, but within that, what I'm really trying to anticipate is that the fact that, okay, for a little bit, now I have this little column trying to fill, right? So we've managed already. We did this kind of dA before, right? That's like our double integral discussion, right? But now, if I take this out, there's my dA component. Now this height, there's like that dz, or I should say just z, but there's a, let's call it z, I guess, right? That dz part of it, right? And so we're going to say that the lowest z is 0, so starting from that xy plane, and now this is our highest, our upper, right? That's going to give us the height of that column. So in the end, it's going to kind of give us this little bit of volume that we're going to kind of fill in. That's it from the lowest z, 0, up until stacking those little blocks. So for myself, drawing these is kind of working with really these kind of columns. And so as we start to draw these, it might be, initial drawing, taking those columns to be these vertical, right, from the xy plane for the base, and then just kind of going the heights with the z. And we want to trap those between two surfaces. We can see, okay, the lowest z value to the upper, okay? But depending, it might be simpler later in other problems. Then maybe we kind of tilt those columns to the side and go from the xz plane out to the y. Okay, or coming out towards these columns, going from the x, or pardon, the y, z plane type of look for your base, and then kind of coming out in the x direction for the heights, for the length part. Okay, so really, if we start to draw these surfaces, these regions, we'll see some examples as we go on, where I try to reorganize, and it's going to really identify how we organize a dv, whether I do dz, dx, dy, or dx, dz, dy. How I reorganize is really going to be based on like that regional virtual integrating, these columns that I use to fill that space to the end, block by block. Okay, all right. So with that said, going back to our problem then, okay, what we had set up before. I'll try to keep it color coordinated for a moment. At first, we're going to do with respect to z, and it was going between 0 and that surface, x times y. Then I would integrate with respect to x next. It went from y to 1. And last, the constants, dy, which went from 0 to 1. So there's our iterated integral. We're going to manage the interior first and work our way out. All right. So integrating with respect to z first, right? Managing that first. Z is the variable. Everything else, constant. So this looks like this integral e to the 1 over y times z dz, right? Just rewriting that if you imagine. If it's helpful, you can imagine that u is equal to 1 over y z du 1 over y dz, right? So that y times du is equal to dz. So with that u sub, then we can always incorporate those limits. E to the u, that dz, y times du. If my lower bound is 0, 0 for z times 1 over y, still 0. Xy times 1 over y z, so z is xy. This is going to go to x now. Integrate here, y is the constant. Integrate 0 to x e to the u du. Y times e to the u. Got x and 0. E to the x y minus y times e to the 0, or y e to the x minus just y, right? Again, a lengthy process, just reinforcing the integration we would have done back in our first semester calculus, second semester calculus. We started to see some integrations by parts necessary later. We could do that. But this is all just that integral set to z. So now we still have that integral 0 to 1 for the dy. This integral from y to 1 of now this expression, y e to the x minus y x dy. Okay, we did the dz already. And again, this will be very similar to integrating There's volume trapped between the surfaces, upper surface y e to the x, lower surface y. Find that volume in that space, okay? Trapped between those surfaces. Now, as we start to integrate, again, this part, previously x is the variable, y is considered constant. So let's start to integrate here. Keep this going, but let's jump into this integral. Y is constant, the integral e to the x is still e to the x minus y constant. It's going to get the variable x attached to it, going from 1 to y dy. Okay. So now, as we continue the integration, calculate when x is equal to 1, y e to the first minus y minus, now on x equal to y e to the y minus x times y square root of y times y. That dy. And now I'm probably going to need another page. Right here, 0 to 1. Distribute a negative, getting rid of parentheses. Right, negative, negative, positive, y squared. That's all, dy. And again, this is e to the first. That's just a constant. Okay. So this one, simple power rule, another simple power rule. The only one that's really going to take some thought, this one, we want to do by parts. Okay. The y, dv e to the y, du is just dy, v is e to the y. I should get a dy, pardon me. uv minus integral v du, right? Like so. Right? So as we start to integrate then, like I said, constant, the integral y, we're going to get a e to the first over 2 y squared minus 1/2 y squared minus y e to the y minus e to the y plus power rule here, 1/3 y cubed, evaluated 1 and 0. And again, thankfully that 1 makes calculation look nicer, and 0 of course as well. So what's that going to become? It becomes for our upper limit, e squared over 1 squared minus 1/2, or e over 2 times 1 squared, 1/2 times that y squared minus 1 e to the first minus to a plus e to the first plus 1/3 times that 1 cubed minus, and for these we'll do that 0 in, okay? But let's jump in here, 1, 1, 1, 1. And when I do those zeros, 0 squared minus 0 squared minus 0 times e to the 0, which is still 0, plus e to the 0 plus, that should be a cube there, 1/3 0 cubed. And so finishing this out, e over 2 minus a half minus e plus e for the first plus 1/3, 0, 0. This one's a minus 1 plus 0. Computing here. Those go away. E over 2, negative 3/2 plus 1/3, negative 9/6 plus 2/6, right? Minus 7/6 there. Long process, I know, and so that's where we'll see a lot of these problems as we go through, right? Technically, in the textbook and so on, you might evaluate all the way. The real discussion is going to be that setup, making sure we can organize how those limits go is going to be much more vital, especially now with the tools we have, computers, calculators, they can evaluate that integral for us, get that exact result much more rapidly than us doing by hand. But again, it's good practice, reinforcing some of those previous concepts. Also gives us a sense of when we do get the results on the computer calculator, that they make sense for us. We're not getting something outrageous that we're just kind of blindly following, but we kind of do have a concept of process of finding on our own, and we do those calculations so that way when we go to use that technology, go to use those software services, so on, that the result we're provided does make sense for us. Okay. All right. I'll try to write out some other examples where we can reorganize and so on. But let's just start with that as our introduction. Okay. So if you have any questions, concerns, definitely contact me. Let me know. All right. Take care. Talk to you more soon.